Good, good. Um, so I was looking at the days left, and it doesn't look like for seniors that you'll be taking the Chapter 15 test. It looks like that probably won't happen for you guys. Yeah, the juniors will, for sure. So seniors, next week I'll have your guys's, I'll start getting your exam review stuff together. I'll be clear as to like what sections in Chapter 15 you're going to be responsible through on your final exam. It's looking like 15.4 is going to be my guess. And then if you want to schedule if you're a senior and you want to schedule your retake, we'll be figuring that out next week. I'll send out or I'll post the form survey, that's what it's called. I'll post a survey next week about whether you want to take a test double or do a retake. But that's my plan for you guys. So I should have a review guide for you guys next week. We'll have we'll figure out the double or retake stuff next week. Try to get those stuff sorted out. So that's a coming. Sound good to you guys?
Yep.
Sure, right?
Yeah.
If you have a boatload of missings or something, and you're planning on making those things up as a senior, you probably should get on that, because the days are slipping away before you can, while we still have chances to do that. We have basically a week of school till spring break, or I'm sorry, 2 weeks until spring break. And then I think after spring break, there's like 2 days of class or 3 days of class or something, seniors, and you're done. So not a lot of class days left. If you're behind on stuff and you need to get caught up, you best get the proverbial nose to the grindstone. All right. Before we get started here, today at the end of class, we're going to be doing the homework quiz. That's over sections 15.1 and 15.2, but we're going to do that at the end. Does anybody have any questions about stuff from there before we get started on new things? Bella. Sure. So problem number 14. Now, problems 11 through 14 are all using the data in this table. So it says, if population growth is exponential, which city and in what year will reach a population of 1 million people first? So I'm going to write 2 exponential models, or I would have already, to do problems 11 and 12. So what I would do is I would say, okay, for Austin, I have the points, my points are T comma P. where T is the years after 1990. So I'm going to have 0, 465,662, and then 10, 656,562. So in like question 11, I would have used this to write a function. So something of the form like P of t equals a times b to the t. So I know right away, because the x-coordinate is 0 for this point, that number is going to be like my a. So to find my b, I would have plugged that stuff in and solved. So b is going to be like the 10th root of something like that. So I'll go to my calculator to do the 10th root. And I'm going to save this value so I can save like all the decimal places. So I'm just going to store that into like the letter B. So I'm going to write my first equation. This one is for Austin. So I'm going to have 465,622 times that value I stored to b to the x. Now I'm going to do the same thing for Columbus. So I'm going to skip some algebra setup steps. I hope everybody's okay with that. So again, I'm going to solve for my b there. And I'm going to store that to, I guess, C for Columbus. Should have stored the other one to A for Austin. That would have made good sense. That's okay. And I'll write my second equation. 632,910. Again, that smaller value is my initial amount because the x is 0 there. So there's that. And then I'll graph 1 million. 1, 2, 3, 1, 2, 3. And we'll set a window. I don't know how long it's going to take for these cities to get to 1 million people, so I'm just going to say like 100 years. Should happen by then, I would hope. My y minimum, well, the smallest y value is this 465, like 460 or 456 or 65,000. I don't want to do that, so I'm just going to type in 400,000. And then I have to go to 1,000,000, but I don't really, I want to do a little bit more than 1,000,000 so that I can see the intersection there. But that ought to do. Let's hit graph. So here's my, oh boy, that was fast. That's Austin. Here's Columbus. There's 1,000,000. So this tells me that Austin got to 1,000,000 before Columbus, right? So I just need to find that value to tell me what year that happened in. So second trace, intersect command. First curve is on Y1. That was my Austin curve. Second curve, now that's on the Columbus curve, so I don't want that. I'll press down. Now I'm on the 1,000,000 line. That's good. Press enter. And then I'll move over for a guess. So my T would be about 22.2. So T would be about 22.2. So I would say during the year 2012, right? Yeah. Austin reaches 1,000,000 first. Something like that. Does that feel okay, Bella? So ideally that you wouldn't have had to do all that work for 14 because you would have written the models already for 11 and 12. You would have just graphed them together and seen which one. So the trick there was just getting a good enough window so you could see everything. Does that feel okay? Cool. Other questions from homeworks or in general? Yeah, Tomasino?
Can you do 9A?
Sure. So when we ask for an initial amount, what time does initial mean? Yep, what time would that, what number of time is initial mean? Zero, right? So to do this, all I need to do is b of 0. So I'm just going to plug 0 into my calculator for t. When I do that, I'm going to get 100. Does that feel okay, Tomasino? So anytime we have time as a variable, when we ask for initial, probably just means you're plugging 0 in for t and seeing what happens.
So is B, plug in 6 for T?
0 for t.
What about for letter B? Like 9?
Oh, so now we'd be plugging in 6 for t, yes. Yep, 100%. Anybody else? Questions? Okie doke. Oh, sorry. Yes, go ahead, Lucy.
Could you just go over one of those like multi-part ones with like the population?
Like number 9 that we just were talking about?
No, like kind of like the one we did with
Okay. Which number?
like 15 is fine.
Okay. So it says the population P in millions of people of Ohio, T years after 1990, can be modeled by the equation, yada, yada, yada. Based on the equation, when was the population of Ohio 10 million? Okay. So I'm going to just start plugging stuff into my calculator. But before I do that, I want to observe what are the x and y variables here and what units are they in. So my x variable is t, right? And that's in years after 1990. And then my y variable is p of t, and it says that's in millions of people. So when I want to type 10 million to my calculator, I'm just typing in 10. Everybody's okay with that? All right. Now I'm going to type this equation in just like the way it's written. So I'm going to use that horizontal fraction bar so I don't have to do like a million parentheses here. And I'm going to set a window. Sure. So again, X is years after 1990. I don't know what the population of Ohio is right now, but I bet in the year 2000 it's north of 10 million. It's a pretty populous state. So I think that 100 is probably fine there. And then this is, I recognize, as a logistic equation, right? So I'm just going to use the horizontal asymptotes as my y min and y max. So one of them is always 0 for a logistic, and the bigger one is just the numerator of the fraction. And that's too specific for me. I'm just going to type 13 instead of 12.79. But that ought to do. Let's hit graph and see what we get here. So that looks good to me. Second, trace, intersect command, enter, enter, enter. So 69.7. So I would say during the year 1969 would be my answer. Lucy, does that feel okay there?
Yeah.
So the trickiest part there was making sure you read the question well and you understood, like, you know, that the y was in millions, so like 10 million is just 10. And that the t is in years after 1990, so like 69 meant 1969. So just making sure you understood what you're reading, but in general, it's, you know, you're typing in the calculator and finding an intersection. Ella? Sure, there's a stack right here. You're welcome to one. There might be one down on the charger too. Yep. So today, what we're going to do for a bit is going to be looking at 15.3. And what we're going to do in 15.3 is introduce you guys to the idea of a logarithm. So before I start like plowing away into like what a logarithm is, I want to try to give you like intuitive sense of the kind of question that we invented this function for. So we know that like 2 to the second is 4, right? And we know 2 to the third is like 8. But what if I wanted to know what 2 to what power is 6? Well, so far what we've done is we've had to graph this onto our calculator, right? So we've done like 2 to the x, and then like 6. We'd like graph it on our calculator. Oh, it's not 6D, 6. And then find the intersection, right? So 2.5849623 or 625, excuse me. Now that's a pretty kooky looking number. In fact, in this case, that's an irrational number. And we're going to give this irrational number a name. We're going to say that this is log base 2 of 6. So it's telling us what power of 2 gives us 6. Because like if I go back to my calculator now and type this in, I get just about 6, right? Why didn't it give me exactly 6? Because it's rounded, right? That 2.58 yada yada yada. I rounded it at some point. That number should go on forever. If I had the entire thing, it would give me exactly 6. Does this feel okay as to like what the idea, what the purpose here is? So what we're going to do is we're going to start by defining a logarithm kind of in terms of an exponential. So what we say is that a logarithmic function is basically just a rearrangement of an exponential function. So given some exponential function where b and x are both greater than 0 and b is not equal to 1, I can rewrite the exponential function b to the y is equal to x equivalently as log base b of x is equal to y. So notice that the base of our logarithm is like the base of our exponential. The exponent in our exponential is the answer to our logarithm, and the answer to our exponential is like the argument of our logarithm. Everybody see how everything matches up? Okay. So let's do a quick example using that definition. So here we've written down some logarithms. And what we're going to do is rewrite them as exponential equations. So the first thing I'm going to do is just put a answer on the end of this, just like we had up here. I'm just going to say that's equal to y. So if I use my definition of a logarithm, I can say 4 to the y is equal to 16, right? And I probably recognize that 16 is 4 squared. And since the bases are the same and the two numbers are equal, that means that the exponents are equal. So that should just be 2. So if I do the next one, we're going to have the base to the y is equal to the square root of 5. Well, I recognize the square root of 5 is just 5 to the 1/2. Again, the bases are the same, so the exponents have to be equal. So y is just going to be 1/2. So again, we have 3 to the y equals 1 over 27. Well, this is a little bit trickier. I recognize that 27 is 3 to the third, right? But if it's 1 over 3 to the third, I recognize that I could make that 3 to the negative third to get rid of the reciprocal. And now, since the bases are the same, the exponents have to be equal. So the next one, we have 12 to the y is equal to 1. Well, hey, I recognize this. I know that any non-zero number to the 0 power is equal to 1, right? So y is just 0. So if I take my last one, log base 8 of 8 is equal to y, that gives me 8 to the y is equal to 8. Well, I know 8 is just 8 to the first. Again, since the bases are equal, the exponents have to be equal. So y is just 1. Does everybody feel okay about this? So from this, I'm going to make a couple of observations. So from this problem, I observe that, yes, sure, that any log of 1 is just got to be 0. Everybody agree with that? From this problem, log base b of b is just going to be 1. If I take the log base matches the argument, then it's just 1. And then from these other 3 problems, what I'm going to observe is a little bit more subtle. So I know that, let's take a look at this one here. We recognize that 16 was 4 squared, right? And somehow that's going to equal, we said that that was equal to 2. What we're observing here is that the log base 4 is canceling the exponent base 4 and leaving me with just the exponent as my answer. So if I collect these properties that we've just kind of observed together, I can say the following. So log base b of 1 is equal to 0 because equivalently b to the 0 is 1. Log base b of b is equal to 1 because equivalently b to the first is just b. This is like our cancel out property that we just kind of showed you, that like log base b is canceling exponent base b. And the reverse also works, that if I raise log, or if I take log base b and make it the power of b, then the exponent base b is going to cancel log base b. And these last two are like a really important conceptualization. This is a really useful way to envision logarithmic and exponential functions, is that they are inverses of each other and they're just going to cancel each other out. Joey. Sure. Now, you know how like we have some radicals that we use all the time? Like the square root, where we have a special symbol for it, where we don't write the index on the radical. Or there's a special exponent that we use all the time where we don't write the exponent down, like to the first power. We never really write the ones. Or a coefficient that we use all the time that we never write down, like 1x, we usually don't bother to write the 1 in front. There's two bases that we use all the time for logarithms that are super common that we don't write down, and we just use a special symbol for logs of that base. Sure. So those two logarithms are called the common logarithm and the natural logarithm. So the common logarithm is just log base 10, and we write just log. We don't bother to write a subscript on it. That tells us that the base is 10. The other one that we'll use all the time is the natural logarithm. That's log base e, and we write the letters ln. Now, when I write ln on my paper, I'm always going to write like cursive ln, because if I write like letter ln, what's the problem with the lowercase letter l when I print it? It looks like a 1. And this is math class, and we have ones all over the place, right? So I'm always going to write it like cursive style so I don't confuse myself. I encourage you to do the same. All right. Let's do a little bit of practice now using these guys. So when I write log, what is really the base there? 10, right? That was the common log. We just got done talking about it. So if I use my definition of a logarithm, then I'd say that 10 to the a is equal to 1,000. And I recognize that 1,000 is just 10 to the third. And since the bases are equal, that tells me the exponents have to be equal. So A has to be 3. Or you could think about it this way. I can rewrite 1,000 as 10 to the third. And since the base of my logarithm matches the base of my exponential, I'm just left with 3. That's the way I prefer to think about them. I think it's a little bit more natural to think about it that way. Plus, it involves less writing. But they're both correct. They're both essentially doing the same thing. All right. So again, I'm going to start by observing that log means base 10. And I'm just going to do this using that second way of thinking about it. The fifth root of 10, I know, is just 10 to the 1/5. So those cancel out, and I'm left with 1/5. You guys feel okay on that? Again, I recognize log is just base 10. How do I write 0.01 as a number with exponent base 10? Well, let's think about 0.01 as a fraction instead. Or no, how about just a scientific notation? Right? We've all had scientific notation in our science classes. What's 0.01 as scientific notation? Just 1 times 10 to the negative 2, right? Or just 10 to the negative 2? Oh, that's perfect. That's just what I needed. Log base 10 cancels exponent base 10. We're left with negative 2. Perfect. The next one is so here the key observation is that you have the natural log, which I know is log base e. Exponent base e cancels log base e, and we're just left with 5. Oh, nice. So next one we have 2 is equal to log of x. Again, I recognize that log means base 10. So what do I have to do to cancel out log base 10? I need to use the exponent base 10. So I'm going to do that to both sides. Now I wrote those 10s really big on a purpose because what I want to emphasize is that we're not multiplying by 10, right? 10 is the base of an exponential, not times 10. Everybody's okay? So those cancel out, and I'm left with 10 squared is equal to x, or just 100. So far, so good. So first thing I observe, I have the natural log, which I know is log base e. Everybody's okay there? Now what's going to cancel out log base e? The exponent base e. So exponent base e cancels log base e. So y is just equal e to the 5th. If you wanted to, you could type that into your calculator and get a decimal, but you don't need to. How do you guys feel so far? Is okay? So let's use the calculator here to do some stuff. So if you have your calculator with you and want to follow along, I'm just going to show you how to type these logs into our calculator. So the first one is log of 7. Notice on my calculator right next to the number 7 is a log button. So just type it in the way it looks on my calculator and press enter, boom. The next one is the natural log of 5. Well, right below the log button is the ln button. Natural log of 5, boom, enter. Now the last one is log base 3 of 19. I don't have a log base button here on my calculator, but I do have the log base command. To find it, I'm going to press the math button. And from the math tab, I'm going to scroll down till I find the log base option. And then I can just type it in just like it looks like on my sheet of paper and press enter. Bam. Everybody feel okay on using the calculator to compute a logarithm? Easy peasy, right? Okay. All right. Now that we kind of understand what a logarithm is, what I want to talk about are properties of logarithms, like how can I manipulate a logarithm? Yes. Sure. So there's 4 properties of logarithms, and really only 3 that we really are going to use commonly. So those first 3 are the product, quotient, and power rules. And what the product rule says is that if I have the product of two things inside my logarithm, I can rewrite it as the sum of two separate logarithms. Next is the quotient property that says if I have the quotient of two things in my logarithm, I can rewrite that as the difference of two separate logarithms. And the third is the power property that says if I have the log of some power, I can rewrite it as the power times the log. So to get used to using these properties, there's going to be two types of problems that we're going to talk about. And after that, we're going to be done with the lesson for today. We'll do the homework quiz and that'll be it. Those two types of problems are going to be like expanding a logarithm and then condensing, or sometimes we call it compressing, the logarithms. So the idea here in an expanding problem is we're going to take one log and turn it into many logs. The other one, we're going to start with many logs and try to turn them into one log. So the order that we're going to apply our properties typically is, when expanding, quotient, product, and then power. And when condensing, we're going to use the opposite order: power, product, quotient. The only exceptions to that would be if you have like some sort of parenthesis going on that implies some different order. Okay, let's do some examples, and that'll be it for today. Good stopping spot. All right. So these are expanding problems, because they say expand. So when we're doing expandings, we're going to be looking for the left-hand side and trying to push the property going that direction. When we're condensing, we're going to be looking for the left-hand side and push it in the other opposite direction. Everybody's okay with that? All right. So if I look at log base 3 of 4x, I'm going to start by looking at the stuff inside the logarithm. And I'm going to look first for quotient properties. Is there anything being divided inside that logarithm? Nope. So none of those. Then I'll look for a product property. Do I see any of those? Is there two things being multiplied inside that logarithm? Yes, right? I have 4 times x in there. So I'm going to use that product property. And that allows me to write this as log base 3 of 4 plus log base 3 of x. Everybody look good there? Okay. Then I'm going to look for power properties. So I'm going to be looking inside each of my logarithms Do you guys see any power properties going on here? Is there an exponent on any of these things? You look very carefully because there's one hiding. Four is 2 squared. Oh, Mr. Kulik, are you serious? I am. Beware those constants. So we can do a power property on that. So the exponent moves to a coefficient, and the other logarithm just stays by itself. And that's as good as we can do. Do you guys feel okay on that? Let's do another. The next one we have is log of 3ab to the 5th. Again, we're expanding. First thing we look for is quotient property. Is there any division going on? Nope. Okay. Next thing we look for is a product property. Is there a multiplication going on? Good. How many multiplications are going on? There's just 2, right? Because I have 3 times a times b to the 5th. That's just 2 multiplications, right? Everybody agree? 3 things are being multiplied together, but there's only 2 multiplication symbols. Agreed? So I can do the product property really just twice. And those 3 things that were being multiplied together are now 3 separate logarithms being added together. Should you guys feel okay there? Next thing I'm going to do is look inside each of these logarithms for a power property. Do you see a power property going on? Where at? Well, 3 is prime. That's just 3 to the first. Can't factor it. 3 is okay, unlike the 4, which was not prime from the previous one. But b to the 5th definitely is 1. So everything else is going to stay the same. So we have log of 3 plus log of a. And then we'll have 5 log of b. And we did a power property there. And that's as good as we can do. So far, so good. It's feeling okay. This usually is, students are fairly comfortable if they just do a little bit of practice. This is not too bad. Okay. First step is quotient property. Do we see division there? Yes. So we'll do the quotient property. That's going to give us natural log of the numerator minus natural log of the denominator. Look good so far? If I look at the first logarithm, is there a product property going on there? Log of 2x. Yes, right? I have 2 times x going on there. Okay. It's going to give me log of 2 plus log of x. How about the natural log of the square root of x cubed minus 5? Is there multiplication going on there? No, right? We don't have 2 things multiplied by each other there. So that guy's just going to stay the same. Now we'll look for power properties. Log of 2, is there a power property there? Agree. No. Log of x, is there a power property there? No, right? How about log of square root x cubed minus 5? Is there a power property there? Great. What is the power? 3 is not the answer. the square root is the same thing as a 1/2 power, right? That's the power for the power property. And that's as far as you can go. Now, Mr. Kulik, I still see an exponent in there. Yeah, but the exponent doesn't apply to the whole thing. If you add x minus 5 to the third, that's a power property. That's not the same as this. There's no power property there because that power isn't around the entire argument. Do you guys see the difference? Okay. All right. Last set of examples, and then we'll do this quiz-a-rooney. Here we're condensing. All right. So condensing, we're going the opposite direction. And as I'm copying this down, I make an observation right away that's a real important one. If I look at the bases of my logarithms, what do you notice? They are not all the same. What does that mean? If I go back and I look at these properties of logarithms, they all need to have the same base, right? So I know that I'm not going to be able to do anything like this is like a separate problem. And then like this, stop. And then like that's going to be a separate problem. You guys kind of see that? All right. So first thing I look for is power properties. So I notice that I have coefficients on those two, so I can do the power properties there. So that coefficient is going to become an exponent. Everybody go okay there? Then I'm going to look for product properties. I notice that, hey, I have addition there, so that's the product property. And that's as far as I'm going to be able to go because I have two different types of logarithms. I can't combine them. At least using those three properties that we were looking at. Okay, my last example. So first thing we're going to look for is power properties. I see 3, right? Now, I'm only going to take the 3, not the negative sign with it. Not incorrect to do that, but I'm going to try. I tend not to like to do it. Notice that when I applied the power property, that power applied to the entire thing, so both the A and the B, so I put a parenthesis around it like that. Or you could have written it initially as like A cubed, B cubed. You could write it that way too. Eventually I probably will turn it into that, but for right now that's where I settled. Now I'm going to be looking for product properties. I see that I do have an addition sign. So what two logarithms am I going to combine together in the product property? it's actually going to be the first one and the last one. Why don't I use the second one? Because it's a negative logarithm. There's a negative sign in front of it. That's tough. Again, I'm trying to give you ones that, in general, I think that condensing is usually conceptually for students trickier than expanding. Expanding's kind of like running downhill. Condensing is kind of like moving uphill. It takes a little bit more effort usually. Now we're looking for quotients. I have that. So the quotient property is going to be the positive part is the numerator and the negative part is the denominator. And if I look at that fraction inside the logarithm, what do you notice we can do there? I can reduce that down and just left with a over b. And that's where we're going to stop here for today. So for homework-wise, we're going to finish this section still, but you guys should be able to do like up through 92, so 37 to 92. Hey, just relax. Some of those are like type this into your calculator. You know, like type the log into your calculator and press enter. They're not all that bad.
37 to 90.